Hello friends, in this video we are going to discuss about the block rotor test of three-phase induction motor. So normally induction motors are widely used in our industries and they consume a huge amount of power. So to improve its performance characteristics, certain design tests have been conducted for this three-phase induction motor, and the design tests namely no-load test and block rotor test. So in this video let us see how block rotor test is going to be conducted on your three-phase induction motor, and we shall calculate the performance, that is the equivalent parameters of the circuit. So generally the block rotor test for your three-phase induction motor or any motor, it is either single phase or two-phase motor, is conducted to know the leakage impedance. So to know the leakage impedance, we are going to conduct this block rotor test on your three-phase induction motor, and further you can also know the motor torque and the short circuit current at normal voltage, and many more parameters can be found from this block rotor test on your three-phase induction motor. So the name block rotor is given because here what we are doing is, here the shaft of the motor is going to be clamped. The shaft of the motor is going to be clamped, that is the rotor or the shaft of the motor is blocked so that the rotor speed is 0, and hence the name, it is blocked rotor. So in laboratories you can block the rotor with the physical hand, and you can conduct this test. So here the rotor is going to be blocked, that means the rotor speed you are getting is 0. So rotor speed is equal to 0 and the rotor winding is short circuited. So now in slip ring induction motor or wound rotor induction motor, the rotor winding are going to be short circuited through slip rings. I am going to repeat that. In slip ring induction motor or wound rotor induction motor, the rotor winding is going to short circuited through slip rings. But in your squirrel cage induction motor, the rotor windings are or rotor bars are permanently short circuited. So the testing of the block rotor test on your three-phase induction motor is a little bit complex, because the resultant value of leakage impedance is going to get affected by the rotor position. It is going to get affected. The resultant value of your leakage impedance, what we are going to calculate from this block rotor test, is going to get affected by the rotor position and the rotor frequency, and also the magnetic flux dispersion, that is the magnetic flux dispersion of the leakage flux path. So due to these three, that is the rotor position, rotor frequency and the magnetic flux dispersion, we are going to conduct our block rotor test on the squirrel cage motor only, because where the effects of these three can be minimized in our squirrel cage type of induction motor. So generally, if anyone asks you why we are going to conduct our block rotor test on the squirrel cage motor only, because of these three factors, that is the rotor position, the rotor frequency and the magnetic flux dispersion, may largely affect in your slip ring induction motor for calculating the resulting value of leakage impedance. So we are going to conduct this block rotor test on cage motors, that is squirrel cage motors. Now if you see the equivalent circuit diagram for your three-phase induction motor, here you are having a stator resistance per phase, this is stator impedance per phase, that is the stator leakage reactance per phase, and this is the shunt resistance, and this is the magnetizing reactance, and here you are having Jx2 dash, that is the leakage reactance per phase, that is the rotor leakage reactance per phase referred to the stator winding, and here you are having rotor resistance per phase referred to the stator winding. Now it has to be kept in mind that when you are performing block rotor test on your three-phase induction motor, it should be kept in mind that you have to apply low voltage only. So by applying only low voltage, we are going to perform this test. So the reason for applying this low voltage, because if you apply the normal voltage, it may burn your stator windings. It may burn your stator windings, so normal voltage is not preferred to conduct this test, therefore we are going for low voltage. And the other reason is, if you apply normal voltage, the rotor may rotate. So the low voltage is applied so that the rotor does not rotate and its speed is 0, and when its speed is 0 you can have the full load current flowing through the stator winding. So to stop the rotor rotating, we are going to apply the low voltage. So the reasons for applying low voltage are these two. The normal voltage may burn the stator windings, and the normal voltage may make your motor to start or the rotor to rotate. So these are the reasons for the low voltage. Now, as we are going to clamp our rotor or block our rotor by physically, so what happens is, if you observe your slip, that is slip is equal to synchronous speed minus actual rotor speed upon synchronous speed. As I am going to block my rotor, thereby your actual rotor speed becomes 0, therefore you are having slip is equal to 1. Now at the unity slip, the load resistance becomes 0, and therefore you can have a short circuit current through your rotor windings, as the rotor bars are short circuited. Now we have to calculate the parameters, thereby we have to record the readings of voltmeter, ammeter and wattmeter. So we are going to have a wattmeter to record the power, ammeter to record the current, that is the short circuit current, and voltage to record the low voltage. So you have to while performing this test, you have to gradually increase your stator voltage, and you have to increase the voltage to a point where you can see the rated current in your ammeter. So once you see the rated current in your ammeter, you can note down the values of your voltmeter, ammeter and wattmeter, so that you can have the corresponding low voltage, short circuit current and the power flowing in the circuit. So once you have these parameters, you can calculate the equivalent parameters for your induction motor, that is 3-phase induction motor. Now here we are going to neglect this shunt branch, because this gives your core loss component, and the core loss component or the core loss of your 3-phase induction motor is very low at this low voltage. So this is very low at this low voltage, so we are going to neglect this branch, and the frictional losses are also negligible as the rotor is stationary. But the stator copper losses and the rotor copper losses are considered here. So if I denote the copper losses, WCU will be given by 3 I0 square IS square into R01. Here R01 is the motor resistance per phase referred to the main stator winding. Therefore I can have my R01 is equal to WCU by 3 IS square. IS is the short circuit current. So now if I say my Z01 is the impedance referred to the main stator winding impedance per phase, then I am having Z0 is the Vs by Is, where Vs is the low voltage measured in the voltmeter and Is is the short circuit current, and from here my motor leakage reactance per phase referred to the stator can be given by X0 is equal to under root of Z01 square minus R01 square. Therefore you can have your X01 and R01 from here. Now to calculate R1 and R2 dash, so here as you are having slip S is equal to 1, this resistance will be R2 dash. So now to calculate R1 and R2 dash, a certain test has to be performed to know the stator winding resistance, and once you know the stator winding resistance, we know that R01 is equal to R1 plus R2 dash. Now once you know R1, you can calculate R2 dash as you know your R01. So we have calculated the motor resistance. Now to calculate the motor leakage reactance, what I am having is, I am assuming my stator leakage reactance and the rotor leakage reactance per phase referred to the stator are equal. Therefore, I can write x1 is equal to x2 dash. Now, I know this x01. From this, I can calculate my x1 and x2 dash by assuming them as equal. So, now if you want to calculate the short circuit current at normal voltage, if I say my V is the normal voltage applied to the stator windings and I am having the short circuit current, that is the short circuit current when we are conducting at low voltage, say Is, and Vs is a low voltage and Is is the short circuit current I want to calculate, then I know from Ohm's law I can write V is equal to K into Isc and Vs is equal to K into Is. So from here you can have your Isc is equal to, if I put my K is equal to Vs upon Is here I can put Vs upon Is, and if I can take that side, so it will be Is by Vs into V. So this gives you a short circuit current at normal voltage. So you can conduct this test at other normal voltages or other low voltages for getting the accurate values of your parameters for the 3-phase induction motor. So I hope you understood well how the test is going to conducted. Please subscribe to the channel. Thank you.